actually hear me? I'm not sure if this.
Yep.
Is this even on? Oh, we have a magical microphone that I can plug into my, not into myself. That would be fixed to myself. So there we go. No, that did not go well. It's cold. I'm tired. Leave me alone. Everyone, I'll go. It's like a that would be boring, wouldn't it? All right. Hey, yeah, you can actually hear me. That's great. Okay. So yes, it's not quite the bits that you leave to the backend normally, but it's going to be bits and pieces in JavaScript that a lot of people keep forgetting. I'm really happy to hear if you know these bits and pieces and use them in your daily work. I would be surprised if you would, but let's see. So, clicker's not working because that's just how the day goes. All right, I'm okay with that. So, quickly about me. Who am I? My name is Martin Splitt, as I have been introduced. It would be easier to not get the last name wrong if we would all be using the Cyrillic alphabet that has a character. So I write it like that, but then I'm like, yes, Cyrillic has it, and then all the conferences in the language regions where Cyrillic alphabet is being used are still doing like the SP thing, and like a split. I'm like, yeah, no, you even have a character to fix this problem. I'm from Zurich, Switzerland. Zurich's beautiful. Switzerland is pretty nice. I mean, our flag is a big plus. I work at a small company called Archaeologic, as I said, and we do like 3D things in the browser. And as you might imagine, doing 3D in the browser requires a bit of, whoops, what's going on here? Requires a bit of work sometimes. I do contribute to W3C specifications every now and then, mostly typo fixes, but hey. No, I did complain a bit about bits and pieces in the web component spec until it got better, and then WebVR is the thing that's going to come up soon as well. I highly invite you and encourage you to also join the journey of making web standards nicer and better, because everything that happens in the W3C and the WG, which are the two standards bodies for web standards, is on GitHub. So you can read it, if you can read, and you should probably be able to. And you can then just make a pull request if there's something that's not good, or just open an issue if there's something that you would like to see differently. And we should definitely do this, because if we don't, then specifications like IndexedDB happen. My slides are a bit screwed up, apparently, but that's OK. I'm a GDE, so that's Google Developer Expert for Web Technologies and Polymer. That means that I get to be your point of contact if you have questions about web technologies in general, or Chrome things or Chrome bugs. I can tell you where to file them properly and stuff like that. And that's quite lovely, because you get to go around a bit. And I'm also helping out Mozilla every now and then. I was part of the launch team from Madrid when we launched Firefox OS. Rest in peace. So yeah, there we go. That's that. So what is this talk going to be about? Because it's a bit cryptic maybe to say like the exotic parts, right? First things first, we're going to have a quick look at a problem that we do not usually solve in web technologies, which is edge detection. That's not about figuring out which browser you're using. It is about finding edges in an image. And then we have a look at how we can tackle this. And first thing is going to be, we're going to do a simple one in JavaScript. And the second thing is going to be, we're trying out web workers instead of this. You might have heard of web workers, especially in the context of a service worker who has heard of web workers as well. And does not mean service worker when they say that. Yeah, that's a different crowd. That's what I thought. Then we're also going to use a different processor for actually solving this problem, which is the GPU, that we luckily have access to thanks to WebGL. And we're going to see what that buys us, or if that's any good, really. And then we're going to have a really, really quick look at WebAssembly. I'm going to explain why it's really, really quick in a second. All right, so edge detection. So what we want to do is we want to take an image, like the beautiful, colorful one on the left-hand side, and figure out where there's an edge, which means some sort of change in color in a certain way that looks like it's not belonging to the same geometrical shape. And then we're going to trace these edges by making them white, and the rest of the image we just turn into black. All right. So the first implementation of this was in JavaScript, and it was very naive. And this is a timeline rendering from that. It's a little small, but you can see that there's a lot of colorful bits and pieces here, and that's not necessarily good, because if you look at it closer, you see that if it starts doing the operation on this particular image, it takes it 2.6 seconds to do something. And if my computer hasn't restarted in the meantime, and it might as well have, I don't know, we'll find out in a second, we should be having a web server running here, and here's an example that demonstrates precisely that. Let me zoom in a bit. Well, OK, great. That zoom is really, really helpful. All right, whatever. The slider gets larger. That's pretty cool. So here we see an image. This is the Frauenkirche in Dresden, actually. Quite beautiful building, has been rebuilt after it has been bombed to the ground at some point. And now let's see. So there's a threshold, right? So how edgy does a pixel have to be to turn up as an edge, as a white pixel? And we can manipulate this value here. I can click here. And then I wait 2.6 seconds. So you see that, right? And it's not that I'm like just waiting for it. And I can click as much as I want. Nothing's going to happen. The world stops, as far as the browser goes. The world stops for 2.6 seconds. And this is all because JavaScript's running. And what kind of JavaScript are we running here? Well, we have to look at all the pixels to figure out if a pixel is an edge or not. And to do so, we're basically applying what's called a Sobel operator. And there's two of them to figure out if it's a horizontal edge or a vertical edge. And as you can see here, basically we apply this to each pixel. And what these matrices mean, that we're looking at all the 6 neighboring pixels. And we do that twice to figure out which. It's a naive implementation. We could obviously kind of like not look at them multiple times because we have similar values in the 2 matrices. But here in this simple variation, we are looking at 12 pixels for each pixel to figure out if it is an edge or not. And we multiply them with these values, with -1, +1, and so on and so forth. And then we add them up. And if it's above a certain threshold, then it is, if it's edgy enough, if it's hipster enough, I don't know, then it is an edge and it's a white pixel. If it's not, then, well, it's not going to be a white pixel. So the first idea is to think, so why does it stop the world? Well, JavaScript is single-threaded. So single-threaded JavaScript means that everything in the browser tab runs in one, well, stream of commands, really. And that includes the UI updates. And that's precisely the reason why the slider stops responding. Because basically, instead of going, all right, OK, I'll run a bit of JavaScript here, and then I update the slider UI bit, it has to kind of wait until the calculations are finished. And these calculations take 2.6 seconds. So I click on something, and then nothing happens. And that's not very good. I mean, there's user studies that have shown that when it's more than 100 milliseconds, people start like dissociating the actions they took, which is the click, and the actions that happen on screen, which is the slider updating. So unless you're super drunk, which we're probably going to be after this conference, you're going to be like, this is not very responsive. And after this conference, we're going to be like, what am I even typing here? But web workers are an idea to give you another thread. So instead of running it all in one thread, most devices today have more than one core. We're basically outsourcing it to another core. So now the browser's first core can actually, or the computer's first core can actually deal with updating our UI, while the other core is actually doing the 2.6 seconds of work. And it looks more or less like this. So imagine that we have a magical little JavaScript file that does the actual edge detection, so we don't have to deal with that. Then we start a new worker, which means we're starting a new process, a new JavaScript process somewhere in the browser that can run on a different processor if it has to. We send over all the pixels because we want to have a look at these pixel data. And then once the calculation in this worker has finished, it sends us a message back with all the pixels that we didn't just going to put into our canvas, and then we are done. You might wonder why there's like pixels and then in an array bracket pixels. The reason for that is the so-called transfer problem. Now, imagine we are having these 2 threads. Who here has done multi-thread programming in some language at some point? Who here has never had race conditions? Very well. That's what I thought. Depending on the language, you might not have had race conditions. But the problem with race conditions is, just to really quickly explain it, if you have 2 pieces of code accessing the same memory, then the order is not defined. So you don't know if something's reading an old value or a new value. And if we are updating this data, then that's asking for trouble, really. So instead of having to deal with something, somehow deal with this, JavaScript or the W3C back in the days decided, you know what, no, we're not going to do that. We're going to have different memory bits and pieces for the different workers in the main thread. So we can't just access variables that we have in our main thread. We have to send the data over. And to send the data over, we can't just say, like, reference this bit over here. We have to copy it. So if we have a really large image, that might be 2, 3, 4, 5 megabytes. If we do that over and over again, then that's going to be a bit of memory that we are spending there. So instead of copying over, we have another possibility, which is transferring it over. So instead of copying the entire blob of memory, what we can also do is we can say, hey, you have access to this bit, and now worker, you have access to this bit, and you do not have access to this bit anymore. So basically, we're just moving it over, losing access in the main thread, which is fine because we're not using this data anyways. So to make that distinction that we're actually moving it over, not using it anymore in the main thread, that's why we have the second parameter, which is this list of things that shall be transferred. Here we transfer exactly one thing, our pixels array. Now what does that buy us? This is now shaded. Great. What does that mean? Is that any better? Well, we are still having like the initial workload. That's kind of what we can't avoid, right? But once we are done and the web worker runs, the main thread is not actually doing anything anymore. And in practice, that means, real quick, that means that we can switch to the other demo, which is this one. And I can now actually, it's quite funny because you actually see the original image every now and then before it's done. But I can now change the slider as much as I want. The calculation still takes 2.6 seconds, but hey, at least my browser UI stays responsive, and that's really nice. Bam, 2.6 seconds. It's still quite painful, isn't it? But as we can see here, we have spun up. So here's our main thread. It's not doing anything anymore. GPU is bored as well. And then we have the edge detection happening on a different thread. There's a dedicated worker thread down here that does the actual JavaScript execution. So we have offloaded work. We haven't made it faster, though. It still takes 2.6 seconds. And this is convenient because this already helps us. If it's something that does not take very long, but happens pretty often, we can still offload it to somewhere else. We can even theoretically divide the work. We could theoretically say, this part of the image and this part of the image, you go to 2 different threads. That would actually make it faster. Not everything is parallelizable, but this one probably is. So that would be nice. There's other things like there's single instruction multiple data proposals for JavaScript or ECMAScript, which would allow us to basically do that without having to explicitly have a worker. It's kind of like hiding it behind the scenes. Then there's also a shared array buffer, which has landed now in ES 2017, or was it in 16 already? I think it landed in 2017, ES 2017. That's basically a structure that does not have to be transferred anymore, but you have to use a bit of magic to actually make it happen that we do not have any race conditions. There's the so-called atomics that you have to run over. We might get canvas access, because right now what we're doing is we're transferring all the pixels to the workers. It would be nice to be able to just say, like, hey, this canvas should just be available in the workers as well, and just as read-only, and we just read off of it instead of having to, move data around or transfer data around. But hey, that is a little farther out because there's a few security implications to this one. And then we have shared workers, so theoretically you can even share workers across tabs. Because right now, if I would open this demo 10 times, I would have 10 different workers and they can't talk to each other. Maybe I just need one that can actually be talked to by all the other tabs as well. So not last but not least, but next idea would be to have a look at WebGL. Because in the end, this is pixel data, and it's a matrix multiplication, and that's what 3D data really, or 3D APIs really are good at. So how about we are actually offloading to the GPU? Because the GPU has thousands of little cores that are not very smart, not very bright cores, but they can do matrix multiplication really fast. Does that buy us anything? First things first, we have to write a bit of code. A bit, right? So this is a GLSL or GL slang code I took from Jaume Sanchez. He wrote a basic implementation of the Sobel operator already. We do that for the horizontal and the vertical edge. Then we're combining the values. And then we're figuring out if it's a white or a black pixel. So that's what these things do. And this code is basically a large function. And we are throwing this function onto the GPU. And the GPU runs this function in parallel on all the pixels. Well, not on all the pixels, but on as many pixels as there are cores available for each of these pixels. So that's really cool. Does it buy us much? Well, first things first, we have the same initial load. We have to decode the image and display the image and all that. And then the GPU takes over. And there's nothing on the main thread, and there's no other threads available. And this is like 800 milliseconds to render the entire image the first time. And then, and then basically nothing, as you can see in the little boxes here. There's lots of little boxes there that actually needs to happen in the background. So let's render, right? Well, OK, this is kind of pointless, but hey, right? So this takes milliseconds rather than 2.6 seconds, which is a bit of a change, I would say. Not only can you do this with image data, you can do this with everything that allows or requires you to run the same instruction on a lot of data, and the operations that are run are non-depending on each other. So that's parallelizable. So matrix multiplications, Bitcoin mining, hypothetically. But that's not working because there's a bunch of interesting blacklisting techniques in the browsers. Damn. So every kind of parallel calculation can theoretically be put in a shader and run on shaders. Not everything, but most of the things can be done like that. But you don't want to write your own shaders probably, and don't want to write, set up a canvas in the WebGL context and all that kind of stuff. So if you don't want to do that, there's Turbo.js, which hides that away from you, and it just says like, hey, run this on the GPU if available. And it falls back, it tries SIMD if it's available. If that's not available, then it runs it with regular JavaScript and workers. So that's pretty cool. There was a wonderful talk from Seth Samuel at last year's JS Congress. Highly recommend that conference in Munich as well. That has all the details on how to do that in more depth. And last but not least, WebAssembly, because I said I'm going to talk about WebAssembly, and it's all over, but the crying. Anyone here playing Fallout? It's from the Fallout soundtrack. Just, play that game. So I said WebAssembly, and I should have known better because I know exactly that the last time I installed the toolchain, it broke, and it took me ages to actually fix it. And I'm like, it's going to be fine. It's 1.0. It's going to be stable. Yeah. Anyway, so WebAssembly, what it gives us is it gives us a binary format. Now, that's not very exciting. We had that with Java and Flash. We all know how that went. Not particularly well, if you haven't read the news in the last 10 years. Or, as Rick would say, Morty, I turned myself into a vulnerability. I turned myself into PDF Rick. So here we have a binary format that runs. Here we have a binary format that runs in the browser. And it works like, it's not meant to be written manually, obviously, because I'm not sure how strong your assembly code, opcode binary skills are, but mine are not very great. So what you can do is you can use a language that does not have, it should be a typed language, it should not have garbage collection. So that renders out a few languages already. But if you have a language that does not need garbage collection right now, like Rust, like C or C++, then you can actually cross-compile these using mscript or LLVM into what's called WebAssembly. There's also a fallback thing for ASM.js, which was a precursor of this, where you use a subset of JavaScript that can be optimized a little better in browsers. But generally, it tries to create this binary file. And the binary file has an advantage of not having to be interpreted and then later on optimized. It can be optimized at compile time as much as possible, and then you just have to run it. The difference between that and Flash and Java and all these things is that we have an API for it. So here we can load it more or less. It's not quite as a JavaScript module, but we load that as a module in JavaScript. We give it the input parameters, we give it the output bits and pieces that we want, and then we get the functions that we can call. We call these functions, get the data back. That's pretty much perfect. and you need the toolchain to make that happen. I would love to show you the demo for this, but my toolchain had a bit of a surprise for me. So I'll just reiterate, really. It gives you a cross-platform binary, which is very, very nice. It's not actually like a native binary. It is a bytecode, just as Java would be a bytecode. But this bytecode is for a stack machine that works in every browser that supports it, and it gives you access to the memory itself. Now, that's a bit dangerous, probably, but it does. The spec is particularly funny because at some point the spec goes, technically you can just go into the memory and do things, and that makes the program crash, but we assume that you don't do this. And that's pretty cool. It allows you to also access the functions that are being exposed by it, so that's quite handy as well. So you can basically have your utility functions and call them from JavaScript. It should get more things. It should get DOM access soon. Right now it's in the MVP stage, so it's at 1.0. Browsers agree. That's a huge step to get all the browsers to agree. There is a more or less working toolchain. I think if you install it clean now, you should be safe. If you've installed it before and were so stupid to actually put that into your system path somewhere, then, well, fun times for you. It works in Firefox, Chrome, and Edge, Safari, hopefully following at some point. And it is supporting the latest version, which is 1 point something. So that's a lot of development going on right there. But it is not quite ready yet for everything. So I've said we do not support the garbage collector languages just yet for interesting and lots of reasons I'm highly inviting everyone. The keen reader shall check out the GitHub repository. It does not have DOM access just yet, so that's happening as well at some point, and it can't be put into like a worker as far as I'm aware right now. Highly invite you to go to the webassembly.org website and check it out, contribute and ask questions and complain about things being broken when they are broken. To sum it up, do not do long-running things on the main thread. That should be an obvious one, but I think it's still tweetable in 2017 because people still do not know this. I've seen far too many things happening on main threads in JavaScript profiles. Not necessarily the best idea. The second biggest pitfall is actually parsing JavaScript. You can't quite avoid that unless you just write less of it. So write less JavaScript. Okay? I mean, we have all the optimizing compilers. They're great. They're wonderful. However, I think we should not write things slowly so that the optimizer makes them a little faster. We can just write less things in the first place sometimes, and then, have them faster from the get-go. WebGL is quite cool for parallel computations. That's useful not only for 3D graphics, it's also very useful for 2D graphics. It can be used for data in any form as long as you can express that as numbers, which all data can be probably expressed at some point, because if it wouldn't be, then it wouldn't be on the freaking computer. So everything that is numbers and you have to run the same instruction on it multiple times, definitely recommend trying to bring that onto the GPU. And WebAssembly is up and coming. It's quite interesting. I'm looking forward to see what's happening there and experimenting more with it. Especially if you have libraries for instance, OpenCV, so it's like the computer vision bits or the machine learning bits that do a lot with calculations on matrices that can be put A on the GPU and B hopefully can be optimized at runtime so that we don't have to parse them in JavaScript first. Right. That gets you going. I'm not sure why I have multiple summaries. Slides are online already. The demos you saw are already online as well, so you have a look at them. Definitely check out what can be done on it. If you have a WebAssembly demo of this particular edge detection bit, I'm happy to merge your pull request, just saying. It's Hacktober, so if you have 4 pull requests and sign up for Hacktoberfest, DigitalOcean sends you a t-shirt and some swag, I think. Highly recommend that one. Happy to help. And yeah, thanks a lot for having me. And now comes the last talk of the day, I think. And then, no questions. Sure, questions first, and then thank you very much for having me here.
Any questions?
Yeah, there's one. Samantha.
Would you, if you're writing C++ to compile it to the browser, are there any changes that you need to make to the code that you write as opposed to writing code for the
It depends is the answer. So hypothetically, no. So you don't have to change your C++ or C code, but the way that C++ is idiomatically written, the same goes for C, is not very easy and very ergonomic to use from a JavaScript world. So for instance, if you're using pointers, and particularly pointers to pointers, so array pointers, that is very interesting because it requires a bunch of hoop jumping to actually get that to work from the JavaScript side if you want to pass in your data. Besides that, you are pretty much safe. Well, besides that, besides having to not write how you normally write C++, you're good.
Can you use WebGL with Web Assembly?
Yeah, I think so. I haven't seen any demos, but I'm relatively sure that, I mean, I'm not relatively sure. I am sure that you can do that. I'm just not exactly sure how performant that's going to be because it then has to take it from the engine parsing that particular bytecode to somehow pass it into the WebGL or the OpenGL subsystem. Not exactly sure how that's going to look like, especially on Windows when you have like the angle bit in the middle. So fun fact, WebGL on Windows for Chrome runs through what's called angle, which is basically translating from OpenGL calls into DirectX, because that's going to be very performant. Definitely try that out, though. Any other questions? That one.
You mentioned a little earlier that the coding has the ability to modify arbitrary memory values. Is that limited to the JavaScript sandbox, or can it start to do really horrible things with the actual browser?
No, it is limited to the sandbox. So basically, the WebAssembly sandbox, the stack machine that it runs in, is given memory, and you can influence how much memory it gives it. And then everything that happens within that memory stays within that memory. It's not like a browser page or something. It's a separate memory page. No. Well, hopefully not. But you know, having seen some security bugs in browsers, but I don't think so. It's a separate page. So unless the paging mechanism in your operating system is broken, you should be safe. Which is also depending on what operating system you're using. Windows. Anyone else? All right, we're good. Thank you very much.